So we are continuing our 4.4 notes with our logarithm properties, but this time we're kind of doing things in reverse. So we are expanding logarithms, which means we're taking them from being neat and tidy and we're trying to make them messy. So I want you to imagine you have your Lego set all assembled and we're trying to break it apart back into the individual bricks. So this is log base 3. We need to pay attention to that and keep it as that. But we're going to use rule number 1 first and then rule number 3 to expand this out into several different terms. So the first thing I'm going to do is insert little multiplication symbols right there so that I can see I'm going to have 3 separate terms that are going to be added together. So if I have a product of logarithms, I add the individual logarithms. Now, I can't really do anything with the x and the y other than this exponent right here can come down. But I can also do something with this because I can actually evaluate log base 3 of 9. It's just 2. So I have 2 plus 2 log base 3 of x plus log base 3 of y. You know you're done when it's as big as it can be, as messy as possible. You don't have any exponents, multiplication, or division left on the inside of the logarithm. So I was able to get rid of all of the multiplication and all of the exponents using rules 1 and 3. Okay, this one, log base 3 of x to the 4th, y to the 4th. Sometimes it's a little hard to see what the exponent applies to, but if I wanted this exponent to apply to the whole logarithm, I would wrap it in an extra set of parentheses like that. And since it's not like that, I'm going to assume that this 4th power applies to the x and the y inside the logarithm. So the first thing I'm going to do is go ahead and bring that down. So I have 4 log base 3 of xy, and then I'll expand that out into log base 3 of x plus log base 3 of y, and then I'll distribute the 4. There's no multiplication, division, or exponents left inside the logarithms, so I know I'm done. Okay, our next one has some multiplication. It has division as well, and this square root is actually an exponent. So we'll start by taking our multiplication problem. So we'll have log of 10 plus log of cube root of x, and then I'm going to subtract log of y. So that takes care of the division. This square root, not square root, but cube root, I'm going to get rid of that and replace it with a 1/3 power. And then I can drop that 1/3 power down as an exponent. So I have 1/3 log of x minus log of y. But remember, log is just common log, so log base 10 of 10 is just 1. And that's as simple as I can get. So another rule that we need to check when we're simplifying is make sure I don't have any square roots, cube roots, any nth roots inside my logarithm. Okay, our last example of expanding is a log base 2. And we have a division, and within the division, in the denominator, have a multiplication. So this is going to be log base 2 s to the power 5. I know those are unfortunate letters to be paired together because they're so similar. Then I'm going to have minus log base 2 of 7, and also subtract log base 2 of t squared. Because this t squared was in a denominator, it needs to be subtracted. So you can think of the subtraction as distributing to both of those terms. And then I just bring my exponents down. So 5 log base 2 of s, subtract log base 2 of 7, subtract 2 log base 2 of t. We don't evaluate this even though there's a number inside, because 7 is not a perfect power of 2, so I'm just going to leave that exact. I'm not going to put it in my calculator and get a decimal for it. So the last idea on this page is the change of base formula. And this is kind of an old, outdated formula. This is when you really need to evaluate a logarithm and you don't have your graphing calculator and all you have is like your phone calculator or an old scientific calculator. All of our newer calculators have these logs with different base built into them. If you have an older TI-83 or 84 that's not the silver edition or the color edition, you might not have it, so you might need to learn this. But this is just a little math history right here. We used to have to do this. You don't really need to anymore, but it's good to know that this formula exists because it can help you understand graphs and equations a little bit better. So the change of base formula says if you have a log base A of B, you can change it to any base. So this C can be any number. Common choices for C would be like 10 or E. And the reason we would choose those is because those are actual buttons that are on the home screen of our calculator rather than being hidden in some menu that you have to search for to find. So what I want you to notice about this formula is whatever was inside in the original expression goes to the input of the numerator. Whatever the base was goes to the input of the denominator, but this C could be anything. So for an example, I could say log base 2 of 7, and I could say I want to change to natural log. So I do natural log of 7 divided by the natural log of 2. But I also could change to common log, and in that case I would do log of 7 over log of 2. And this is not the same thing as like log of 7 over 2. So what we were doing in our previous things was when we had a log of a quotient, we would split it apart. But this is not the same thing. What this is doing is it's saying evaluate the individual logarithms and then divide them. Whereas what we were doing in our logarithm properties, we were dividing first and then taking the log. And those are different things. So we're going to prove this change of base formula. And we're going to prove it by solving the equation a to the x equals b in two different ways. So the first way is we are going to solve a to the x equals b by taking a log base a of both sides of the equation. So I have a to the x equals b, and I am going to take a log base a of a to the x of both sides. So I'm doing the same thing to both sides of the equation. And on this side, this is a perfect cancellation because log base a says, hey, what's the exponent on a that gives me this answer? Well, I can see the exponent. It's staring me right in the face. It's right there. So this left-hand side simplifies just to be x. And the right-hand side is log base a of b. And that's as solved as I can get because I don't know what a and b are, so I just kind of have to leave it like that. Okay, so let's box that out. That's my first way of solving and my first answer. The second way that we're going to solve is we're going to take log base c of both sides. Let me do that in color like I did the last one. So I had a to the x equals b was my original equation, and we are going to take log base c of both sides. And you would go, well, why would you take log base c when this is a base a? And again, maybe it's because you don't know what you're doing, or you want to use one of those buttons on your calculator that are easy to access. So since this base and this base don't match, all I can do is use rule 3 to bring this x out in front of the logarithm. So now I have x log base c of a equals log base c of b. And to solve for x, I just divide by everything that's not x, which is this whole mess right here. So x is log base c of b divided by log base c of a. Okay, these were the same equation. I solved them the same way. I have two different answers for x, but by the transitive property of equality, my conclusion should be that if I take the log base a of b, that should be the same thing as the log base c of b divided by the log base c of a, which is exactly our change of base identity.